We'll complete our journey through Module 2 with a consideration of structural isomers. Now you'll notice that the word isomer is similar to isotope, but it is a very different sort of animal in the chemistry world. We'll find out more about it presently. Our learning goals for this video are to understand the similarities and differences between constitutional, sometimes called structural isomers. We'll also want to see if there is a systematic approach to building a family of constitutional isomers. I want to start by talking about building alkanes. An alkane is simply a hydrocarbon molecule that contains only carbon and hydrogen, and it has only single bonds, that is, sigma bonds. Examples of this would include things like methane, which has one carbon, ethane, which has two, and propane, which has three. Okay, these are very simple molecules. They're just linear carbon chains with hydrogens attached to all the other positions where carbon doesn't have anything else to attach to. All right, so these molecules are pretty unambiguous in that there's only one way you can draw these molecules using the building blocks. Now you'll notice that when we go from methane to ethane, we basically have added a CH2. When we go from ethane to propane, we've also added a CH2. We can think of this as inserting that CH2 into one of the bonds in the molecule to create a new structure. Let's see how this looks. So let's look beyond propane. Now, when I have a molecule like propane and I want to insert a CH2 somewhere, it turns out there's two ways I can do it. One of them is insert it into one of the end bonds there, or I could insert it into one of the middle CC bonds. We'd get the same thing out of it, a linear chain of 4 carbons. But there's another way I can insert this, and that is to put it into a carbon-hydrogen bond on the middle carbon. When I do this, I'm going to create a fundamentally different structure. Let's see what it does. So in the first case, I'm going to end up with a linear chain of 4 carbons. That is a molecule called butane. If I insert it into the second place, though, I don't have a linear chain, I've got a branch chain. In other words, I've got 3 carbons that can form a straight chain with a carbon hanging off the middle of those 3 carbons. All right, again, the formula is going to be C4H10, but this molecule now is called 2-methylpropane. So this leads us to isomers. These two molecules, butane and 2-methylpropane, are different molecules, but they have the same formula. That is what defines an isomer. Any molecules that have the same formula but have different structures or molecular properties, either physical or chemical, these are what isomers are. Constitutional isomers, their difference between the two isomers is they differ in the way the bonds are connected, that the atoms are connected together. So we're going to use bond line diagrams just because it's a little bit easier to see what's going on here. So now you know why we introduced bond line diagrams in the last video. It's easier to draw and it's easier to visualize these constitutional isomers because we don't have all the extra stuff hanging around, all the extra cabbage on the carbons. We can extend an alkane chain by simply adding a new line segment. Okay, so we have to connect the new carbon to something on the old chain. So we just connect a new line segment to one of the endpoints on that old chain, and that creates a new isomer. So for example, here's propane, and again I'm numbering those atoms 1, 2, and 3. So I can add it to that line segment to the first carbon atom, and we'd end up with that. I could add it to the second, and we would end up with that. Or I can add it to the third, and we would end up with that. Now I hope you can see this, but these two ones on the top and the bottom are actually structurally equivalent. They are both straight chain hydrocarbons. They represent the same molecule. They would not be in any way different in the laboratory. But the one in the middle is different. It's structurally distinct because now the carbons are not connected to each other in a straight chain, they're connected in a branch chain. So let's extend this one bit further and try to figure out what the pentane isomers are. So we're going to start with these two isomers that involve 4 carbons and add one more carbon to each of them and see how many different structures we can make. That would represent the number of isomers that have the formula C5H12. So in the case of the straight chain butane, I have 2 types of carbons that are really distinct from one another. I can either have a carbon at the end of the chain or one of the 2 carbons that are in the middle of the chain. As I will argue that the two blue carbons are functionally the same thing. They are equivalent to one another, as are the two yellow carbons. They're functionally equivalent to one another, but they are different from each other. Similarly, for the 2-methylpropane, the 3 carbons on the ends are all functionally equivalent. They're bonded to the same sets of atoms, and the carbon that's in the middle, the purple one, is also bonded to 4 atoms, but it's bonded to 3 carbons and 1 hydrogen, so it is in some sense structurally different from the other 3. So what happens when we add another line segment to each of these points? Well, in the case of the straight chain, I can add it at the end to one of the yellow carbons and I'll get a straight chain pentane, or I can add it in the middle and I'll get a branch chain. Okay, so I hope you can see that these are equivalent to adding a carbon to one or the other type of carbon in the 4-carbon chain. Okay, in the case of the branch chain, I can add one at the end, okay, to one of the 3 equivalent carbons that are colored green, or I can add it to the middle, and I end up with a highly branched chain molecule out of that. So the 2 in the middle, I hope you can see, they're essentially equivalent molecules. They are the same molecules. They don't represent distinct isomers. They are the same isomer. Our 3 isomers then are pentane, 2-methylbutane, and 2,2-dimethylpropane. And these are 3 different ways that we can organize 5 carbons and 12 hydrogens together to make different isomers. Now when we go to longer chain hydrocarbons, well, sometimes they're not long chain, sometimes they're highly branched, but you can see that the number of isomers grows dramatically as we add more carbons. So when we start with methane, ethane, and propane, there's only 1 isomer possible. With butane there were 2, with pentane 3, there will be 5 with hexane, and that will grow up to 75 for decane, which has 10 carbons. So you can see that this is quite a dramatic shift and quite a large number of isomers. So why should we care about this? Why have I spent all this time talking to you about what isomers are? Well, first of all, these structural isomers have different physical properties. So that could mean that they have different melting points and boiling points. It could mean that they have different density. They may have a different charge distribution or a dipole moment associated with them. It implies, most importantly, that the elemental constitution, in other words, the molecular formula of a molecule, does not uniquely define it. The way it's connected together defines it as a particular molecule. So it's important to know a molecular formula, but it is not enough. We also need to know the bond connectivity. And this is something that you'll get to explore some in the second lab exercise this semester. So keep it in mind. We'll see lots of examples of isomers, both structural and other kinds of isomers, as we go through the course.